Hi, welcome. I'm Gaurav Jagaukar, Enterprise Solutions Architect at Amazon. We'll be discussing various compute options that we have on AWS for microservices. But before we get started, let's discuss how we've reached the microservices era. One application pattern perhaps many of you have experienced and hopefully put in your past is the monolithic architecture. Here, a holistic application is deployed as a single unit on shared infrastructure. Its tightly coupled components perform many different functions and are maintained by many different development teams. Deployments are extremely risky and disruptive. If any component's deployment fails, the whole deployment must be rolled back. So deployments rarely occur and require intense amount of centralized approval and coordination. I'm not saying monoliths are bad, but a lot of organizations that need agility are looking for better ways to package applications. So moving from monolithic applications, one of the most popular architecture patterns for many years is the service-oriented architecture approach. Here, components are decoupled and communicate with each other via web service APIs. The picture is one of the most common examples of a service-oriented architecture, the multi-tiered architecture or an entire architecture. In it, user experience is delivered on the front of the application by the presentation tier. The core business logic resides on the server side as a part of the logic tier, and any data that needs to be persisted by the application resides in the data tier. This pattern allows for really important things. Amongst other, infrastructure is decoupled, so deployments can occur independently, and scaling and resource consumption can be managed independently. Development teams can now be specialized. Now teams can be filled with developers that can be specialized with skill sets that are well suited for the area of application that the team owns. What you're left with is smaller ownership and deeper, less broad technical skills. So a faster process and smaller, more stable, frequent deployments could be achieved. The microservices architecture. Finally, a pattern that has become very popular in the last few years is the microservices architecture. Here, the same tenets that apply to a service-oriented architecture are still valid, but components are broken down into smaller, single-function modular web services so that the benefits of SOA amplified throughout the architecture. If you're working in a centralized organization today that's happy supporting monolith organization, this might look a bit complex to support. But remember that in order to support the move to SOA or microservices, there will have to be a similar breaking apart of the deployment and the development processes to recap the full benefits. Because things have been broken apart, you may have small development teams whose responsibility is limited to just these pieces of the application. So how does this look in real life? This is exactly what you would see on our Amazon.com page. Each component that you would see is a microservice, like the product catalog, the shopping cart, product reviews, frequently brought together experience, other sellers, and many more. This whole experience is carefully designed to make it simpler, but offer a great amount of detail when you make a purchase at Amazon. Now let's talk about how you can implement it today on AWS. So to start with Elastic Beanstalk, you can quickly deploy and manage applications in the AWS cloud without worrying about the infrastructure that runs these applications. AWS Elastic Beanstalk reduces the complexity without restricting the choice or control. You simply upload your application, and Elastic Beanstalk automatically handles the details of capacity provisioning, load balancing, scaling, and application health monitoring. Elastic Beanstalk supports applications developed in Java, .NET, PHP, Node.js, Python, Ruby, and as well as different types of containers for each language. A container defines infrastructure and software stack to be used with a given environment. When you deploy application, Elastic Beanstalk provisions one of many AWS resources like AWS EC2 instances. The software stack that runs on your Amazon EC2 instances depends on the container type. But when you're doing microservices, you're speaking of a single area of responsibility, the single responsibility principle by itself. A microservice or the team that caters to it does one job and does it very well. Fine-grained execution environments are what you're worried about. What you're also looking about is better isolation that allows for component cohabilitation. The thing that you get at the end of it is faster initialization and execution. So why not do it using containers? What is a container? A container image is a lightweight, standalone, executable package of a piece of software that includes everything that is needed to run it. Code runtime, system tools, system libraries, and the settings involved. If you want to run the containers on the cloud, it's easy. You spin up some EC2 instances, launch containers on them, and get going in minutes. This would work even better if you're using dozens of containers. But if you think about it, scaling this, managing hundreds of instances, monitoring their health, scaling them, and launching your containers on them, and a whole life cycle around them. How do you scale to that size? It was just 3 years ago that we announced the release of Amazon Elastic Container Service. We launched ECS because our customers needed a way to manage the scale and the deployment of Docker containers on AWS. Our customers wanted a managed service where they didn't have to operate their own cluster, a solution that was scalable, secure, that they could use and trust to run their production workloads. And then they wanted to tight integration with and support for EC2 features that they had already liked and used. Then we focused on building a highly reliable and a performant Docker image registry and announced this GA release at the end of 2015. Our goal with ECR was to enable developers to use the same familiar Docker push-pull APIs to store the container images and see this product highly adopted by customers, both running containers on AWS and really across any environment. But let's focus on the other three today. So let's say you plan to run several highly available applications across 3 availability zones. ECS enables you to be able to operationalize your containerized workloads at very high scale. No management software to install or worry about its own high availability. The cluster management piece enabled you to be able to monitor the cluster, scale it using auto-scaling groups, and be able to manage the state of the instances in the cluster. The placement engine enables you to be able to set rules to the target landing zone of your containers on the right instances, and that is based on your preferences. And then finally, the advanced scheduling features help maintain the desired state of the application, spawn new containers to automatically respond to your scaling needs. And then, of course, maintain resiliency by deploying across multiple availability zones while being resource aware of the underlying compute. In the last couple of years, we've seen a great adoption of production use cases on Amazon ECS. Our active users are up by more than 450% since 2016, and we are managing containers across millions of instances each month. In fact, we are witnessing an incredible transition to containers and customers of ECS, whether it's Expedia running its travel platform or Mapbox powering mapping data for some of the most popular websites. Amazon ECS enables the customers to be able to run containers at scale. And indeed, we see hundreds and millions of containers launched every week. Kubernetes is a portable extension, open source platform for managing containerized workloads and services that facilitates both declarative configuration and automation. According to a recent CNCF survey, 63% of respondents run containers on AWS. But our customers told us, hey, running Kubernetes isn't a trivial work piece. And we think we can better spend our cycles focusing on our applications. They also said if we had things our way, we wouldn't have to think about the nuances of Kubernetes deployment or configuration. We wouldn't have to worry about managing etcds or the masters. So what we did is we built Elastic Container Services for Kubernetes, also known as EKS. And we built it around only 4 tenets: platform to run production-grade workloads, native and upstream Kubernetes experience, seamless integration with AWS services, and the EKS team actively contribute to the upstream environment. Now with EKS, the complexity of standing your own Kubernetes control plane is simplified. Instead of running the Kubernetes control plane on your account, you connect to a managed Kubernetes endpoint on the cloud. This endpoint abstracts the Kubernetes control plane. Your worker nodes can check into the cluster, and you can interact with the Kubernetes cluster through a tooling that you're already comfortable and you already love. All this while, we've been discussing how to get our compute options. We've still got a bit of underlying server management to do. So let's talk about how to use Fargate with ECS. You want to think about Fargate as a technology and not a different service per se when you're using ECS. That is, there are no APIs for you to learn. With Fargate, you have no instances to manage, so no more patching, OS, or runtimes. With the new task-native API, you don't need to worry about the clusters. They are an organizational and a security boundary at best. But you don't need to do cluster utilization or auto-scaling of compute resources within the cluster. With the resource-based pricing model, you only pay for the resources that you provision with each task. We think Fargate fundamentally changes how you think about your consumption, how you will run and deploy your application with containers. Here's a screenshot of ECS when you define an application called as a task definition. You're presented with an option to select compatibilities with a launch type. Essentially, Fargate is just a launch type. If you want to run your containers on EC2 instances registered with your ECS cluster, that's the EC2 launch type. So Fargate clusters are heterogeneous. Say you have different requirements where your notification app team would like to be able to move to Fargate, but has a different timeline plan to do so, but are ready to use your Fargate for shopping cart and web apps. As you notice, you can run the web and the shopping cart apps as ECS services with launch type as Fargate, and you only see your tasks across the various subnets and AZs. You can continue to run notification apps as EC2 launch types within the same cluster as the Fargate-powered web app and network boundaries, thereby applying uniform set of policies in terms of IAM permissions as well as network access rule. Notice how the containers are spread across the different subnets across AZs. This gives high resiliency and fault tolerance to your microservices. And on the topic of serverless, let's go to AWS Lambda. AWS Lambda lets you run the code without provisioning or managing servers. You pay only for the compute time that you consume, and there's no charge when your code is not running. With Lambda, you can run code virtually for any type of an application or a backend service, all with zero administration. Just upload your code. The Lambda takes care of everything required to run and scale your code with high availability. You can set up your code to automatically trigger from other AWS services or call it directly from any web or mobile app. The serverless computing approach that brings Lambda isn't about not just having to manage servers. Serverless means having a simple but a usable primitive, your code as a Lambda function, with nothing that looks like a container or server. The programming model and the API are all oriented around dealing with functions. Serverless means you only pay for the work done and not for provisioning capacity. You don't have to worry about the utilization. You never pay for idle. You only pay for the compute time, that is, the time that your function takes to run, in the units of 100 milliseconds. This is something that most of our customers get excited about, thinking about what 21 microseconds for 100 milliseconds of compute can do for their cost. For example, a publishing company from Singapore tells us that they saved over $30,000 per month by switching from a proprietary image processing solution to the one that they built on Lambda for processing millions of images a day. Which brings me to the third aspect, that is serverless means that the scaling is already built in. You can never over-provision or under-provision your resources. Since your code is run in response to events, Lambda will automatically spin up as many instances of your function as are required to handle any incoming event rate. Let me repeat this. We have customers running backend handling in excess of 100,000 transactions per second at peak, and others like AdRoll who are processing over 55 billion ad impressions per day using Lambda. Last, and not the least, of course, serverless means that the functions come with high availability, and depending on the workload, fault tolerance comes built in. The combination of offloading these responsibilities can have a significant impact on the way you own and operate the applications running in the cloud. Let's discuss about how we go about using AWS Lambda. First, your software is able to respond to events in real time. So data stores, state changes on EC2, or created alarms on CloudWatch, or bring your own event through API Gateway or the SDKs. The second part means that you are able to continuously scale. This means it is automatic. You don't need to be provisioning servers all the time. And then you don't have to think about deployments and code runtimes at the machine level. You just pay for how long your code runs for, and this allows you to handle instantaneous and ephemeral types of application. And this was not really possible previously, was it? And it's easy to use Lambda. Bring your own code, write it in your favorite programming language like Node.js, all the versions from 4.3 to 8.10. Use Java 8 or Python from 2.7 to 3.6. You can now also use .NET Core 1.0.1 or 2.0. And if you've watched the latest reInvent, you can now use Golang. And then, of course, you can bring in your third-party libraries, use Maven or Gradle or tools of your choice for that. And then this comes with only one dial for you to tune. Select the memory. You can choose all the way from 128 MB to 3 GBs. The CPU and network are allocated proportionally. Lambdas are easily integrated with other services. So you either invoke your Lambda directly in sync or async mode, or it is completely event-driven. So an S3 put, DynamoDB streams, Kinesis, or CloudWatch events, all of that is supported, and many more. The other part that we need to understand is the flexible authorization. Securely grant access to resources and VPCs through the Lambda function, and then also give a fine-grained access control to who can invoke your Lambda functions in the first place itself. Further talking, authorizing functions, you could use Cloud9 editor or just upload your pre-written code as a package zip. And of course, we've got third-party plugins for your favorite IDE like Eclipse or Visual Studio. Monitoring and logging is pretty much very important. Now, how do you do it in the serverless ways? Metrics for requests, errors, and throttles are available to you on the dashboard itself, and built-in logs are provided through Amazon CloudWatch logs. The programming model, however, remains the same and the one that you're used to. So you can use processes, threads, 500 MB of /TMP, sockets, and all of that normally. And then we've got the SDK built in for Python using Boto 3 and Node.js. You have to keep in mind, however, that the applications are designed to be stateless. Process the data using external storage like Redis or your favorite data store. And don't assume any affinity to underlying infrastructure. We've discussed the compute side of services with AWS. However, we still need a perspective of the spectrum of services that are available to you. So what we're going to talk about is the concept of region and availability. So I'm hopeful that you're already comfortable with it. To make HA on EC2, what you have to do is deploy across availability zones. On managed, there is an option for multi-AZ. In serverless, HA and fault tolerance is taken care for you. First services that were available on AWS about 11 years back were SQS and S3, serverless services by themselves. Lambda was added as a compute to S3 because our customers gave us a feedback. And then we added sources to Lambda. This provides a whole spectrum of serverless for you, from chatbot, IT automation, web applications, and Alexa, amongst many others. Microservices provide you agility. For that, you have to ensure that your entire continuous integration and continuous deployment pipeline is set. Remember that with AWS, infrastructure is code. CloudFormation helps you spin infrastructure, including network components like VPCs, subnets, and security groups. Now you can version control the configuration, execute these services like code pipeline, and use AWS Code Deploy for deploying to a fleet of EC2 servers, or even Lambda. Make sure that you also get introduced to a little squirrel called SAM, Serverless Application Model, where you can define resources optimized for serverless. The AWS SAM extends CloudFormation to provide a simplified way of defining the Amazon API Gateway APIs, AWS Lambda functions, Amazon DynamoDB tables needed by your serverless application. Keep in mind, it's an Apache 2.0 project which builds on the CloudFormation script. Previously, CloudFormation lacked the specialized resources and types optimized for defining serverless application. Now with SAM, you can use resource types to write CloudFormation template that defines your serverless resources only with a few lines of code. How do you get started? You'll find a wide diversity of application for SAM and serverless application repository, which consists of scripts and code for you to get working on. To create serverless application using SAM, first you create a SAM template. It's a JSON or a YAML configuration file that describes your Lambda function, API endpoints, and other resources that you need in your application. Then you test, upload, and deploy your application using the SAM local command line interface, the SAM CLI. During deployments, SAM automatically translates your application specification to CloudFormation template, filling in the default values for unspecified properties and determining the appropriate mappings for invocations. So the permissions to set up for any Lambda functions are built in. It will refer to your Swagger definition for the APIs part to build it. Monitoring the services, especially if they are serverless, is another thing that we got asked very often. X-Ray is a service that provides an end-to-end view of the requests as they travel through your application, and it shows a map of your application's underlying components. The service maps let you see the relationship between all the resources within your application, and that too in real time. You can quickly see where the high latencies are occurring in your application, and then drill down into the specific services and paths that are performing poorly. So you might ask, how does X-Ray do all this? What X-Ray does, in a sense, is X-Ray captures the trace data from the code running on EC2 instances, also ECS containers, beanstalks, API gateway, Lambda, and many more. It implements follow the thread tracing by adding HTTP headers to requests that don't already have one, and then pass the header along the additional tiers of request handlers. The data collected at each point is called as a segment. It is stored as a chunk of JSON data. A segment represents a unit of work and includes request and response timing along with optional subsegment that represents smaller units of work. It can be as deep as the lines of code if you supply the proper instrumentation. Then a statistically meaningful sample of the segments are routed to X-Ray service, which in a sense is a daemon process that runs on EC2 instances inside containers. The segments are then assembled into traces, which is groups of segments that share the common ID. The traces of segments are then further processed to create a service graph, which is visually depicted the relationship between the services to each other. Today, we've discussed and compared various compute options that are available to you when you think of microservices. We've covered a range from elastic beanstalk to containers and going all the way to serverless. If after today you want to take AWS knowledge to the next level, you have several options available to you. To gain more confidence and hands-on experience with AWS, watch our instructional videos and explore the self-paced labs. Additionally, you can attend an instructor-led class by qualified AWS instructors and learn how to design, deploy, and operate highly available, cost-effective, and secure applications on AWS. And remember to validate your technical expertise with AWS certification. AWS also has a wide partner ecosystem to help you focus on your success and take the full advantage of all the AWS business benefits that AWS has to offer. To learn more about the APN partners and find the right one that fits your needs, please visit the AWS APN booth at our showcase. I hope you enjoy the rest of the AWS Innovate online conference. Do take the time to provide feedback on today's event so that we can keep improving on the event experience. Have a great day.
Hi, and welcome to This Is My Architecture. I'm Dave, and I'm here with Barry from Vanguard. Welcome, Barry. Usually I ask people what their company does, but I know what you guys do. You have my money.
We're a small financial investments company.
Yeah, but you're growing all the time. And,
we sure are.
You're facing some unique challenges because of that, and it kind of all starts at the DB2 database, right?
Right. At the moment, DB2 is our crown jewels. Every night we process trillions of dollars through that system, and basically keep everyone's records reconciled.
So how do we get that data into the cloud so we can do cool things with it?
Well, as a part of that processing, DB2 writes a transaction log. So basically, we take the data from that transaction log using a CDC tool, CDC meaning change data capture. So every change that happens gets recorded out here, and then we can push it from the on-prem system out into a CDC distributor, which is located in Amazon.
Okay, so now we've moved the data up into Amazon Web Services, right? What are we trying to do with it now? I see RDS, I see Dynamo. Is there a method to our madness?
Absolutely. We have a number of different lines of business, and not one size fits all. So, for example, one of our lines of business is really interested in continuing to use relational technology.
Okay.
So what we can do is from the CDC tool, we can push the data directly into Amazon RDS, where it meets the same schema that we have in DB2 out there. And then the microservices can be written to pull the data from RDS directly. And that meets the requirement for the microservices to own their own data and represent that within a bounded context.
But not so fast with DynamoDB, right? Like, do we have to make some changes?
Absolutely, right? So the CDC tools at the moment aren't capable of writing directly to DynamoDB. And even if they were, we wouldn't necessarily want the schema that they might use. So what we're actually looking at the moment is pushing data from the CDC into a streaming data platform.
Okay.
And once it's in that streaming data platform, we can look for messages going into it and then use our own logic to translate those relational changes to the format that we would want to see them in the NoSQL DynamoDB database.
Okay, and then our microservices can feed off Dynamo?
Absolutely. So the microservices there would be written to talk to their bounded context, which exists within DynamoDB.
Now we've got the microservices talking to their database of choice, right?
Yep.
But this kind of opens up some things. You mentioned you guys are growing like kind of all over the world now, right?
Right. So we have offices in London and in Sydney. We want the customers there to have the same experience that they would have if they were in the United States. So for example, we can use RDS read replicas and push the data directly from what we call our hub data center out to any number of spokes, one of which we'd expect to be in Sydney, one in London. The data would be pushed from DynamoDB into a read replica out there using DynamoDB streams as
Okay,
well.
so we put the data close to the users, right? And now this opens like opportunities for us to, be able to access that anytime,
Yep.
anywhere, and really support your growth.
Absolutely.
Okay, awesome. Thanks for coming and talking with us, Barry.
Thank you.
And thanks for watching This Is My Architecture.